Okay, so welcome everybody to the second edition of Semiva. So, thanks. So it's a seminar organized by PhD students, and this year we will have two seminars, and one concerning spectral algebraic geometry, which is not this one, and this one will be about Kähler geometry and especially Calabi conjecture and its consequence. So it will be 5 seminars starting from today. And our first speaker is Letizia Branca. She's gonna give a brief introduction to Kähler geometry and the properties we will need to the further seminars. So please, Letizia.
Hello, everyone. I'm going to give an introduction about Kähler geometry. Particularly, I will first recall some definition concerning also the Riemann curvature tensor, and then I will focus on Kähler geometry and Kähler manifolds and their properties. So let us start with just some definitions, which will be useful during the seminar. And okay, let's start with the definition of a PQ tensor. We said that a PQ tensor, we consider a vector space V. A PQ tensor is a multilinear match P, which goes from V times itself to times its dual, which I will denote by V star, P times. Particularly, we will need this definition because we are going to work on manifolds which are endowed with a metric. And particularly, we say that a Riemannian metric G on a smooth manifold M is a tensor field of type P02, which means that we're going, for each point P in M, we're going to associate to P the bilinear map GP, which goes to from a vector space, which in this case will be the tangent space at P times itself inside R. And this tensor field is symmetric and also positive definite, which means that when we take x and y in the tangent space of P, we just get G of xp, yp, and being symmetric means that we can switch the order of x and y, and positive definite, when we take an x which is not 0, we have that gxx has to be greater than 0. Okay, so another important definition is the definition of a linear connection. So we're going to consider a Riemannian manifold, which is a couple given by our manifold and the Riemannian metric on our manifold. And we say that a linear connection nabla is a smooth map which goes from the smooth vector fields on M. With this symbol, I will denote with those vector fields on M, which are smooth, times itself inside the smooth vector fields of M. And it has to satisfy the following properties. The first one, which is the fact that let us consider x, y, x1, x2, y1 and y2 smooth vector fields, and also they have to offer each smooth function of M. So we have that first, we have that now x1 plus x2 of some y has to be equal to now x1 of y plus now x2 y. Second property, we have that now x of y1 plus y2 has to be equal nabla x of y1 plus nabla x of y2. Third, we have that nabla x of fy has to be equal to x of fy plus f nabla xy. Moreover, we also have another property, which is the fourth one, which tells us that when we take nabla of fxy, this one is equal to f nabla xy. Particularly, there's an important theorem in Riemannian geometry, which states that when there exists a unique connection such that the following two properties are satisfied. The first one is that, let us consider x, y, and z vector fields. We have that the connection is torsion-free, which means that when we take nabla x y minus nabla yx, this one has to be equal to the Lie brackets of x and y. And the second property is that the connection is compatible with the metric, which means that when we consider x of g by z, this one is just g of nabla xy, z plus g of y nabla xz. Okay. This connection is called the Letizia connection. I will denote it by LC when I will recall it. And it is really, really important on a Riemannian manifold because thanks to this connection, we can define a tensor, which is both a 1-3 tensor field, but also 0-4 tensor field. And this tensor is called the Riemann curvature tensor. And the reason why it is so important is that it encodes all the information about the curvature of a Riemannian manifold. So let us define this tensor. So, definition, we consider a Riemannian manifold and we consider nabla, the Letizia connection, and M. Then we say that the Riemann curvature tensor associated to nabla is just the multilinear map arc which goes from the space of smooth vector fields of n times itself 3 times. This one is the 1-3 version of the Riemann curvature tensor. Inside the smooth vector fields of n. And it is defined as follows. So we consider x, y, and z smooth vector fields. Then we have that arc of x, y, and z is given by nabla x, nabla y of z minus nabla y, nabla x of z minus nabla of the Lie brackets of x and y of z. But as I mentioned before, there's also a 0-4 version of this tensor. In fact, in this case, we call it Riem, and in this case, it's a multilinear map which goes from the smooth vector fields of m times itself 4 times inside the smooth functions of m. And in this case, we have that we consider x, y, Z and W in vector fields. We have that cream of W, Z, X, and Y is defined as G, where G is our Riemannian metric of R, X, Y, Z, W. Okay, so thanks to this definition, we can define also another tensor, which is the Ricci tensor. This tensor is a 0-2 tensor field, so and it will be really important in the last part of the seminar because we are going to define a two-form out of this tensor, which has some peculiar properties on Kähler manifolds. So let us define this tensor. So for each point on our manifold, we can consider a basis, let M be the dimension of our manifold. Of the tangent space at P. Then we define the Ricci tensor of X and Y, where X and Y are smooth vector pools in M, as the sum over I, which goes from 1 to the dimension of our manifold, of Riemann, EI, X, EI, Y. Okay, this operation is called taking the trace of the Riemann curvature tensor. So we're taking its trace, we're taking the sum over I of Riemann EI, X, EI, Y. And we obtain this tensor, which is a tensor of type 0-2. Okay. So now I will recall some definitions concerning complex manifolds, just in order to then arrive to the definition of Kähler manifold. So first we consider M. Keep this definition in mind because it will be useful later. A smooth manifold of dimension 2M. Then this manifold is endowed with what it is called an almost complex structure, and which is a linear map, which goes from the tangent space of M to the tangent space of N, such that when we apply J to times, we obtain minus the identity. Particularly when M is a complex manifold, we can consider this almost complex structure is called complex structure. And particularly, in general, this map induces the decomposition of the complexified tangent bundle of a manifold of dimension 2M. In fact, we have that the complexified tangent bundle can be rewritten as the sum of two subbundles, which are denoted by T01 of M plus T01 of M. And particularly when M is a complex manifold, we can consider local coordinates Z1, Zm, where these are just some x1 plus I y1, and so on till xm plus I ym. And these two subbundles have some local sections which are given by those I will call as del over del z alpha, which are holomorphic sections, which are defined as d over dx alpha times on half minus d over dy alpha with the I. And here we will have local section b over dz beta bar, which will be given by 1/2 d over dx beta plus I d over dy beta. Okay. However, when we have this complex structure on our complex manifold, it also induces a linear map over the complexified bundle of one forms, and in particular, this bundle decomposes as the sum of two subbundles, which I will denote by lambda 1 0 m plus lambda 0 1 of m. Okay, and we can also take what the exterior k power of these two subbundles, and in particular, I will denote by lambda k 0 of m the k exterior power of the first one, and lambda 0 k of m the k exterior power of the second one. Particularly, we will define as lambda pq of m the space given by lambda p0 m times lambda 0 q of m. Okay, and this decomposition induces another decomposition, which is the decomposition of the complexified bundle of k forms over m, which rewrites as the sum over p and q such that p plus q is equal k of the lambda pq we have just defined. So something which is interesting is that in the real case we have a way to go from k forms to k plus 1 forms, which is using the exterior differential. And in this case, we define two new operators, which will be the operator, two new operators, which will be the operator del, which goes from pq m inside lambda p plus 1 q of m, and the operator del bar, which goes from lambda pq of m inside lambda pq plus 1 of m, such that v rewrites as del plus del bar. We also have the fact that when we apply d to a form eta, which is in lambda 0 1, I will denote by lambda eta 0 1. This one has to be 0, and the bar of a 1 0 form is equal to 0. Note that the fact that b rewrites as the sum of the two of them, and the fact that b squared is equal to 0 implies that b squared is equal to del bar square, which is equal to del bar equal del bar del, which has to be 0, and it's direct consequence of this fact. Okay, I will also give another definition here because it will be useful later, which is the definition of the double cohomology. We define with the HPQ del bar the cohomology space given by the quotient of the kernel of del bar, which goes from lambda pq of m into lambda pq plus 1 of m over the image of del bar from lambda p q minus 1 of m inside lambda pq of m. Okay, and this and particularly, as for the complexified bundle of k forms, we have that the cohomology group HK and C is isomorphic to the sum p plus q. This one holds on on Kähler Manifolds, I have out. I will tell you later. But well, this one rewrites as it also induces a decomposition, but I think it's better to talk about it later. Just keep in mind this other decomposition. So we have these HPQ cohomology groups, which will be our global cohomology. Okay, so now we're ready to give some definitions, some more definition, but talk about Kähler manifolds. Okay, so we want to talk about Kähler manifolds. So let us consider a manifold M, a complex manifold. And let us consider G, a metric on M. Then we say that G is an Hermitian metric on M if it satisfies the following property. G of xy has to be equal to G of jx, jy, for each x and y vector fields of M, where this J was our complex structure. So we will denote by MGJ an Hermitian manifold. Which is a manifold endowed with a metric, which is Hermitian. Particularly when we have an Hermitian metric, we can also define an Hermitian form, which is a two-form defined using G and the complex structure J. Particularly, we have that our two-form omega of x and y will be defined as G of jx, y, where x and y for each x and y vector fields on M. Okay, so one has these two forms, and one can note that it satisfies some properties. Particularly, since this equality holds, we have that omega xy is equal to G of jxy, which is equal to G of j squared x y. But j squared was minus the identity. So here we have G of minus gx jy, but G is symmetric, so this one is just minus omega y x. Moreover, one can also show in a similar way that omega of xy is equal to omega of jx jy. It follows from these properties that our two-form is indeed a real one form. Moreover, we can write omega locally in this way. By definition, it is given by I, the sums over alpha and beta, such that G alpha beta bar dz alpha wedge d zeta beta bar, where this G alpha beta bar are just G applied to B over dx alpha, B over d z alpha, z beta bar, where the d over dz alpha were those sections for those components of the complexified vector bundle T10, and the other one were sections for the other component of the complexified vector bundle. Okay. One may ask himself if one has a one real form, can reconstruct in some way our metric using the form. And the idea is to construct in this way. So construct G of xy, taking omega of xjy. But to do this, one omega has to satisfy an important property, which is the property of being positive, which means that omega of xjx has to be greater than 0 for each x which is not 0. In fact, when we defined our Riemannian metric, we said that it is a metric if it is at 0 to tensor, which is symmetric and it is positive definite. So this property has to be satisfied. So we're now ready to give the main definition of the talk, which is the definition of Kähler manifold. So let us consider and J and a Riemann manifold. We say that G is scalar if omega, which is also called the Ricci form, the omega is equal to 0, which means that omega is closed. In this case, we will call omega Kähler form. Okay. So there's also an equivalent way to see if a manifold is a Kähler manifold. In fact, we have the validity of the following proposition. We consider an Hermitian manifold MJ, and which is Hermitian. Then we have that G is scalar if and only if nabla J is equal to 0. And this condition is also equivalent to require that nabla omega is equal to 0. So one can note that an apparently weaker condition, which is the one which requires the omega to be 0, implies a stronger one, which is nabla omega equals 0. Of course, in this case, one can show that nabla J equals 0 implies nabla omega equals 0 using the properties of J, which is the fact that the properties of J and the definition of omega. While on the other side, one has to work a little using, once again, the properties of J and the fact that omega is closed. But what it is really cool, I would say, is the fact that the omega, which is apparently weaker, implies something which is stronger in some way. But why are Kähler manifolds so interesting? One of the main reasons why Kähler manifolds are that interesting is the fact that we can, in some sort of sense, define what is called the Kähler potential. We can define what is called the Kähler potential. And to see this, I will recall two important lemmas. The first one, which is the local I del bar lemma. Okay, let us consider M a complex manifold. And we consider omega, which is a 1-1 form over M, but it is also a real 2 form over M. Then omega is closed if and only for each point on M there exists U, a neighborhood of our point, such that when omega is restricted to this neighborhood, it can be written as some I del bar of phi, where phi is the real function on M. Okay. Let's see a sketch of the proof. On one direction, the implication is trivial because when we write omega locally as an I del bar of some phi, then we can apply d to I del bar phi, and just recalling the fact that d is del plus del bar, and the fact that del squared is equal del bar squared, which was 0, and also that the del bar plus del bar del is equal to 0, one can show that this coordinate is 0. On the other side, we need to recall another lemma, which is the so-called del bar Poincare lemma, which is the equivalent of the Poincare lemma for the real case. In fact, this one states that a del bar closed zero-one form is locally exact. Then using the lemma, one can show the other implication. Okay. But there's also, and using the lemma, we can conclude the proof. There's also a global version of this theorem, which is of this lemma, which is the global del bar lemma. We will consider a manifold which is compact and also Kähler. And let us consider eta a smooth real exact 1-1 form. Then there exists a phi real function on M such that eta rewrites as some I del bar phi. So the main difference is that here, of course, it is global, while in the other case it was just local because we had the presence of this U for each point. But what it is really interesting is that we have just given the definition of Kähler manifold. We have said that a manifold is Kähler if its Hermitian form omega is closed. Therefore, we have a 1-1 form, which is also a 2 real form, which is closed. But this implies that locally, our form can be written as I del bar of some phi, some real function phi. So by the local I del bar, we have that the Kähler form omega is locally equal to I del bar of phi, for phi a real function, and this phi takes the name of Kähler potential. Note that when we look at a form, at a 2 form, which has this form, we have that in cohomology, I del bar of phi is equivalent to the class of 0. However, on Kähler manifold, the Kähler metric the Kähler form is linked to the volume form. In fact, omega m, which is omega wedge product itself m times, is equal to m factorial, the volume form of the metric. So we have that the cohomology class of omega cannot be 0 in H2 of m. So its cohomology class is not 0. So we can find the local Kähler potential, but we cannot. We can find the local Kähler potential, but we cannot find the global Kähler potential. Moreover, we have also the validity of the following lemma, because one may ask himself, okay, what happens if we have Kähler metrics on a manifold, and if the cohomology class of the Kähler forms are the same. Lemma. Let us consider M a complex manifold. And let us consider G1 and G2 Kähler metrics. On M, if the class of the Kähler form associated to G1 is the same as the class of the Kähler form associated to G2, then there exists a unique function, real function phi, such that omega 2 rewrites as omega 1 plus I del phi, where this function is unique up to a constant, of course. Okay, so we have seen some properties about Kähler manifolds. We have seen that they have some reasons for which they are so interesting. Let us see some examples. Okay, first example. The flat metric on Cm. Okay. When we were talking about Hermitian metric, we said that the Hermitian form locally rewrites as omega, which is equal to I, the sum over alpha and beta of G alpha beta bar, dz alpha, wedge dz beta bar, where G alpha beta bar was just G applied to d over d z alpha d over d z beta bar. So we recall also that this d over d z alpha were just 1/2 of d dx alpha minus I d over dy alpha, while in the case of dz beta we have another 1/2, so here we have 1/4 d over dx beta plus I d over dy beta. Okay, so now we're on CPM. So here we have that using the fact that G is a bilinear map, this one gives us 1/4 2 times delta alpha beta. And the reason is that when we take the product between d over dx alpha, d over dx beta, this one is equal 1 if alpha is equal beta, otherwise it gives us 0. The product of d over dx alpha times d over dy beta gives us 0 because the two of them are different. So the same happens for d over dy alpha. So we get 2 times d delta over d delta alpha beta. So this one is just 1/2 delta alpha beta. Hence here we get I over 2 the sum of over alpha of dz alpha wedge dz alpha bar, which is just I over 2 del del bar of the logarithm of the modulus of z squared. So this one is our Kähler potential. Hence, we have an example of the Kähler metric. But we can also give another interesting example, which is the Fubini-Studi metric on CPM. Which is a complex projective plane. And in this case, I will just give you an idea. If one wants to see more details about this metric, can look on Moriano's notes about Kähler geometry. In this case, we know that when we have the complex projective plane, we have a projection which goes from Cm plus 1 minus 0 on CPM. And we define another map U over Cm plus 1 minus 0 in R. And it associates to a vector z, z1 squared plus z2 squared and so on. Okay. And okay. Okay. So here we have this one, and we can consider the map. We can consider the one for alpha defined as the logarithm as I the bar of the logarithm of u. And this defines a two-form on this space, which is not positive definite, hence it is not a Kähler form on Cm plus 1 minus 0. However, there exists a unique one form omega, such that p square omega is equal alpha. And this omega is defined over CPM, and it's a 1-1 real form. And particularly, one can define a metric, the Fubini-Studi metric, as omega of x, j, y. And it is possible to show that this one is positive definite. So it defines the Kähler metric. Okay. Before seeing other properties concerning Kähler geometry and particularly Kähler manifolds, I'm going to give you some more definitions concerning complex vector bundles and particularly complex line bundles, which are vector bundles of dimension 1. And also, I will give you the definition of the so-called Ricci form, which is defined out of the Ricci tensor, which was the one we mentioned at the beginning. So we recall that the Ricci tensor of x and y was a 0 to tensor field for x and y, which were smooth vector fields on n. Particularly on a Kähler manifold, it satisfies the following equality. we have that Ricci of xy is equal to Ricci of jx, jy for each x and y. And we can define a two-form using this tensor in the following way. We define rho of x and y as Ricci of jx, y. Okay. For x and y. Particularly, one can see that as we have seen for the Hermitian form, also in this case, we have that rho of jx, jy is equal to rho of x and y. And we also have that rho of xy is equal to minus rho of yx. And this tells us that rho is a real 1-1 form. 1-1 form. Okay. It's a real 1-1 form. And in particular, we have that locally this form rewrites as rho as minus I del bar of the logarithm of the determinant of the matrix whose entries are G alpha beta bar. Okay. So keep in mind this definition of the rich tensor because it will be useful later. As I told you before, we have these two forms, and this two form has some properties for Kähler manifolds. In fact, it has some topological properties in some sense. Okay. Let us talk a little about complex vector bundles, and let us see why we need them in order to talk about the Ricci form. So, a complex vector bundle on a complex manifold M is given by a map phi which goes from a complex vector bundle of rank K. A map of complex manifold pi which goes from E to M. And second factor, for each point P on M, there exists the neighborhood and the neighborhood of the point. And map phi U, which goes from phi minus 1 of U inside U times CK. Okay, note that thanks to the property 2, we have that each fiber over a point is isomorphic to CK. Particularly, a linear vector line bundle is a complex vector bundle of rank K, of rank 1. And we will be noted by L over M. Moreover, we also define an Hermitian metric on a line bundle. In fact, we say that an Hermitian metric on a line bundle is the choice of an inner product on each fiber. So it's just take a point P on M. We take an inner, we choose an inner product on a fiber of P. So HP, which goes from its fiber, which I will denote LP times LP inside C. And this inner product has to be symmetric, and it has to be linear in the first entry, antilinear in the second one. And when we take H of V U, it has to be equal to HUV complex conjugate. Moreover, we have that H of U has to be greater than 0 for each U, which is not 0, where these U and V are just sections over the fiber. So at the beginning, we talked about connections, and we mentioned the Levi-Civita connection. But there's also a way to define a connection over a line bundle, and a connection over a line bundle. In particular, we say that the linear connection is just a math number which goes from the smooth section of the complexified tangent bundle of M times the sections of L inside sections of L. And it has to satisfy the following property. First one, we have that nabla x of F sigma, where sigma is a section over our bundle and x is an element in the complexified tangent bundle, has to be equal x of F sigma plus F nabla x of sigma. Moreover, we also have the validity of the following: nabla x of sigma is equal F nabla x of sigma. Okay, so particularly there exists a unique connection nabla, which I will denote nabla C, you will see in a moment why, such that first it is compatible with the metric H, which is just a generalization of what we have seen before when we said that the Levi-Civita connection was compatible with the Riemannian metric. So here we have that given x of h sigma 1 sigma 2. This one is equal h nabla x of sigma 1 sigma 2 plus h sigma 1 nabla x sigma 2. Okay. And the second condition is that when we have a section which is locally holomorphic, then we have that nabla b over dz beta bar of sigma has to be 0. And this connection is called the chair connection. Note that this one is different from the Levi-Civita one, since while in the case of the Levi-Civita connection, we had a connection which was both compatible with the metric but also torsion-free. While in this case, we have a connection which is compatible with the metric but it is not torsion-free. So when we compute the torsion, that one does not vanish. Okay. When we looked at the Levi-Civita connection, we defined the tensor, which was the Riemann curvature tensor. which was really important, which is really important on when one talks about Riemannian manifolds, because it helps us understanding the curvature of the manifold, because it encodes all the information about it. However, also in the case of a general connection, one can define a curvature, particularly the curvature of the shared connection is the two form omega h in gamma complexified bundle of two forms of M times endomorphisms of L, defined by omega h of x and y of some sigma equal to nabla chi of x, nabla c of y, sigma, minus nabla yc, nabla xc of sigma, minus nabla brackets of x and y of sigma. Okay, so it's defined in this way. And particularly, one can show, for this part, to see more details about this part, I would tell you to look at Vyachelovsky's notes called the Japan Lectures. We have the validity of the fact that first we have that omega h is in gamma, one can show that is in gamma 1 of M. And second, we have that given sigma locally non-vanishing holomorphic section then the curvature locally rewrites as minus I del del bar without an I but the minus del del bar, the logarithm of the norm of the section squared with respect to the metric. Okay. And particularly there's a validity of the following proposition. Which tells us that let us consider a line bundle then the form I omega h is a closed real 1-1 form. And the first Chern class of the line bundle defined as I over 2 pi of the class of omega h inside h11 of M, which is contained in h2 of R, is independent on the choice of the metric. So let us see a proof. First, we know that for any function, F, we have that when we take I, the bar of F, this one can be written as follows, recalling that when we apply that bar 2 times, this one is equal to 0. So we can just rewrite del plus del bar of minus I del bar F. Okay, but then we can rewrite this one, if one recalls that also this squared is equal to 0, as 1/2 del plus del bar of minus I del bar F plus I del F. Okay, but this one is just 1/2 B, because this one is D, and here we have this I with plus and minus and the del bar and del. So here is just D, J, where J is the complex structure, F. So using this fact on our manifold, on our connection, on the curvature of the connection, we have the following fact. We have seen before that locally can be written in that way. So we're in a similar situation, just multiply times I. So we have that minus I of omega h is just, it's minus I del bar of the logarithm of some section, norm of a section squared, which is locally non-vanishing. And this one is minus 1/2 d j d of log sigma squared norm with respect to h. So it follows from this fact that I omega h is real and also closed. Moreover, when one works on a line bundle, thanks to some properties of the transition functions, it can be shown that taking another metric h tilde, then there exists a smooth function f, which goes from m into r, such that h tilde can be written as e at power minus f of h. Therefore, the connection of h tilde is just I, the connection of h tilde is just I, the connection of h, plus I del bar of f. And as a consequence, one has that the cohomology class of I h tilde is the same as that of I omega h. So this concludes the proof of this proposition. And we're now ready to state an important theorem. So why we have done all this stuff? The reason is that the first Sharon class is strictly linked to the Ricci form. And that is the reason why we're talking about a topological meaning of the Ricci form. Since we have seen in here that this class does not depend on the choice of the metric in cohomology, and particularly we have the validity of the following theorem. Let us consider K, which is the canonical bundle of M, which is just lambda and 0 of M. And then one has, and let us note by omega K, the connection of the canonical line bundle. Then one has that the curvature of the canonical line bundle, the curvature, of course, of the canonical line bundle. Then one has that the curvature of the canonical line bundle multiplied by I is equal to minus rho. So there is a link between the two of them. And as a consequence, one has that, we have seen it before, the first Chern class of the canonical line bundle is just the class defined as I over 2 pi, the class of omega k, but this one is minus I times I, which means 1 over 2 pi, the class of the Ricci form. So the two of them are the same in cohomology, and that is quite a big fact. That is something important. So let us conclude the seminar with some curiosities about Kähler manifold, particularly concerning their cohomology. At the beginning, we had talked about the double cohomology, and I recall here the definition. We said that HPQ, the bar, was just defined as the care of the bar from lambda PQ of M inside lambda P plus 1 Q, QP, Q plus 1 of M over the image of del bar lambda PQ plus Q minus 1 of M lambda PQ of M. Okay? Well, on a Kähler manifold, one has that HK of MC rewrites as the sum over P and Q, such that P plus Q is equal K of H PQ del bar of M. Moreover, we also have that HPQ del bar of M is isomorphic to HQP of M. Therefore, we have that the Betti numbers Bk, which is just the dimension of Hk and C, can be written as the sum over P and Q, such that P plus Q is equal K, of the dimensions of these other groups. So VPQ of M will be the dimension of HPQ of M. So it will be given by the sum of these numbers, and particularly we will also have that VPQ of M, thanks to this fact, is equal to VQP of M. Okay, and as a consequence, we have that odd Betti numbers, so B2K plus 1 are even, so it's equal to L for some L. And that's something which is kind of interesting. So with this curiosity, I finished my seminar. I hope you enjoyed it, and I hope you had a nice time, and thank you for the attention.
Okay, thanks, Letizia, for the nice seminar. I don't know if there are any questions or comments here in presence or even online. So feel free to speak now or remain silent, I guess. So no questions. Okay, if not, thank Letizia again.
Grande Leti!
And also, I remind you that the next step of this seminar will be on May 3rd, I guess, with Filippo. He will talk us about of holonomic groups and he will prove, let's say, prove the Berger classification, and we're related to Kähler Manifolds. So 3rd of May, and the other section of Semiva will start, I guess, on the 30th of April. So the spectral algebraic geometry seminar will start that day. And thank you very much for coming, and see you next time.